So this is the first time I've done a screen recording of my computer screen to go over PowerPoint slides for one of my lab videos. This is the first time I've done it like this, and I hope it works for you. So let's get into it. Okay, this lab is going to be a simple demonstration of Newton's laws of motion, along with, of course, the kinematic equations of motion. Now, this is going to be done using an Atwood machine, and I thought to just give a little bit of background on Newton's laws of motion and the Atwood machine before actually doing the experiment. Here are the laws of motion, the first law, second and third law, and these are pretty well straight translations from the original writings of Newton himself. We will encounter them, in particular the first and second law, for this lab, and I will explain it a little bit more, of course, as I go through this background introduction. Okay, so hopefully after I've gone through this lab with you guys and some of the background information, you won't feel like little Calvin here when he was asked to explain Newton's first law of motion in his own words. So hopefully you'll have something better to say than Yakafu ma grug puba wap zink watum gazork chumble spuds. That was his own words. And maybe you won't need loopholes. Now, here's a couple of, like I said, historical little background notes. Newton actually defined inertia, but Newton defined it as a tendency of an object to maintain a state of rest or uniform motion. And here is one of the main issues that come up are that the Atwood machine contraption, the machine itself, solves or helps to mitigate. The issue is, of course, that when you drop an object, it falls very rapidly in the absence of much air friction, and you can't time it, especially, you know, back in the 18th, 17th century, they didn't have digital clocks, and so it would fall very far, very rapid, and no one could really reasonably time it, and so it was very difficult to make meaningful measurements. But Galileo was famous for dropping objects off of the Leaning Tower of Pisa. At least that's what legend has it. And he supposedly did a famous experiment showing that lightweight objects fall at the same rate as heavy objects if they don't have too much air friction. Any air friction difference, then it makes it seem often like the lightweight objects will be falling slower. For instance, a feather or a piece of paper compared to a metal or a wooden ball. Well, obviously, the air friction is acting much stronger, and it makes the lightweight object, the paper or feather, appear to have slower acceleration due to gravity. But if you take out air, then you can find many nice videos online about removing air and showing that lightweight and heavy objects fall at the same rate. Anyways, that's Galileo. Again, the issue that we're most interested in and relevant to the Atwood machine is the fact that they just fall too fast to measure. So this is the original diagram of what Atwood himself may have used at the Cambridge Trinity College in the 18th century. He came along about 40 years after Newton. What it allows us to do is measure the rate that objects are accelerating due to the force of gravity and nothing else. Particularly if you say object B here is falling, and it's falling slow because it's attached to object A by this pulley, and object B only has a tiny bit of excess mass, and the tiny bit of excess mass has to move both objects A and B downward due to the force of gravity and nothing else. That's the idea. That's the main idea in the Atwood machine lab. And if you set this up right with a tall enough contraption here, you can measure the distance of course, and the time. That's what this pendulum is here for. So it can measure the time as the object falls. Of course, we don't have to use pendulums. That's our main improvement over this old contraption, is that we have modern day digital timers, which makes it much easier. But the key again for the Atwood machine is that it causes the object to slowly fall compared to Galileo when it dropped very rapidly. Now Galileo, on the other hand, he would, realizing that he couldn't time an object falling, he did an object rolling down a ramp, just like you guys' experiment with the I want to say Matchbox cars, but with the Hot Wheels cars. They're rolling down the ramp, and that makes a small enough acceleration that it can be measured. Now Galileo used a ball rolling down a ramp, and he used a water drip timer. Imagine that. You had to time you did timing by how many drops came out of a container. Okay, well, he was able to get his results for the acceleration due to gravity, similar to what you guys are doing for the lab that will also be due this week in addition to this Atwood machine lab, and that's the free fall down a ramp. Now let's go on here. So this is demonstrating numerically what I said a second ago, that the time for an object to fall a long distance is very short. So 4.91 meters is how far an object would fall in 1 second, and that is almost 15 feet. So you have to get up on a ladder 15 feet high to be able to measure about 1 second of time. That's not easy given human reaction time and all those types of factors. So obviously if you wanted 2 seconds, well, you got to go up, well, that's 19.6 meters. That's going to be nearly 60 feet or so. So that's very impractical. And what we're going to use, though, is the Atwood machine and the simple kinematic equations of motion to be able to relate the acceleration that's observed on the Atwood machine to the acceleration of gravity. So that's what AEX here, that's acceleration from experiment. And from those simple kinematic equations, the definition of acceleration is a change in velocity divided by the time during which that change occurred. If it's a constant acceleration, then the velocity is changing at a constant rate, and it's going to be equal to the slope of this graph right here. Okay. We also know from kinematic equations that for linear motion, the average velocity is going to be equal to the distance divided by the time. You just have to know the total distance that it traveled, okay? Because it can be faster or slower, but on average, this is what it is, and because of that, you'll go this distance in this amount of time, okay? Okay, so I'm not going to be able to go through all the kinematic equations. Hopefully you guys are getting the hang of those very nicely from the first chapters that you've already been tested on. Here is the other kinematic equation that we have. What we basically want to do is get this acceleration, okay, and we need a change in the velocity with time. Well, the initial velocity starts out at 0 before you start the object moving, and the time, of course, starts out at 0. So that makes finding the change in velocity pretty easy if you can figure out what the final velocity is, v. Okay, so the initial velocity is 0, and the final velocity, v, from this simple definition right here of the velocity average, is going to be 1/2 of that final velocity. Okay, so you can look at this graphically, right? The final velocity, was, say, 10 meters per second, or 10 miles per hour, and the initial velocity was 0 miles per hour. Then, if you're going constant acceleration from 0 to 10, then the average is going to be 5 miles per hour, 1/2 of that final velocity. Okay, I hope this little bit of background helps a little bit, and we shall move on to the rest of the notes that are relevant specifically to the Atwood machine. Now, keep in mind the goal is to get this experimental acceleration from the values that we measure with the Atwood machine. Well, we can measure the distance that the object falls easily and the time that it takes for it to fall. And then we can calculate the average velocity of the object that was falling. And then when we have the average velocity, through the simple kinematic equations that, like I said, aren't terribly intuitive, but nevertheless, you can get the final instantaneous velocity as twice the average velocity. Now, you'll use this one also for your ramp experiment with the Hot Wheels car. So same kinematic equations as linear constant acceleration kinematic equations. Now we can have the instantaneous final velocity and the average velocity, and then, well, look what this is. Acceleration is a change in velocity with time. So if it goes from 0 to the final velocity v, then the change is just going to be the final velocity divided by the time. Okay, so that will give us the experimental acceleration. Now, that's what I'm showing right here. Okay, the final velocity divided by the time, and that is of course equal to the slope for this constant acceleration graph, velocity versus time. When this acceleration is the one that is observed for the masses that are moving in the Atwood machine, then it can be directly linked to g, the acceleration due to gravity. And this is done through Newton's laws of motion. So that's what chapter 5 is all about. At least it was chapter 5 in my edition of the book. So that's why this is up here as 5.11b. This is 2.7 because this was from, of course, the previous chapter with the kinematic equation. Here's a little quiz. There's a lot of good quizzes like this throughout the notes, just pure conceptual quizzes to see if you're starting to get conceptual, intuitive feeling for these concepts. Hopefully you are, but this is just the old feather and a rock. If you evacuate all the air so there's no friction, then what rate will they fall comparatively? And they will fall at the same rate. So you can look up videos of that online, I'm sure. I don't have any handy to include right here. Don't want you breaking the laws of physics. That's flagrant disregard. It won't be tolerated. So there you go. Here we go. Newton's first law of motion is the law of inertia. This is dealt with in the lab when we're talking about the pulleys, the inertia of the pulleys, and the idea of friction. Galileo didn't really think that objects would remain moving forever in the absence of something stopping them, force that is stopping them, like friction. Aristotle. Aristotle thought that the object would stop moving after being pushed all by itself. So Newton and others, of course, said no. The object will keep moving indefinitely unless friction acts on it to stop it. Okay? And that's what you see in space. If you just very, slightly push something, you look at the astronauts in absence of gravity, and the things just move through at a constant speed. They don't seem like they'll ever stop until something pushes them in the opposite direction. And so the first law is just the law of inertia, and we'll have to deal with that a little bit. There's a silly little cartoon on that. Here's a little qualitative question for you to test your understanding of it. So that's Newton's second law of motion. The most famous form is F is equal to ma. Force is equal to mass times acceleration. Okay, so we're going to use that definition. So again, these qualitative questions, you can go through those. Hopefully they will help out a lot. They should, if you really look at them and think about them. But here we're back to Atwood's machine. It's a prime example of Newton's second law. So as I said earlier, they're connected by the pulley, as you'll see in the experiment in a minute here. On the left here is m fall. That's what it's referred to in the lab handout. It has extra mass so that it's heavier. And Nevertheless, because these two masses are connected, again, one of the key points here is that the net force that is, downward on the heavier side has to move all this mass. So if it's just a tiny bit of extra mass on the left-hand side here, then it will have a small force. But if there's, no friction, it can move all this mass. But because it's a small force, what's the acceleration going to be? Well, if you look back at Newton's second law here, of course, force is equal to mass times acceleration. If it has a small force and a large mass, well, that's what was up here. Small force and large mass, acceleration is going to be small. Okay? The small force is going to be the small bit of extra mass on the Atwood machine that is causing everything to move, but the larger mass is both sides of the pulley, the total mass that the extra weight is moving. So that's the idea. Okay. So let's look at it again. Now the net force is just that little extra bit of mass, and I call it m fall. Okay, that's a little bit of extra mass that causes everything to move. Now you take that little bit of extra mass and say, well, what's the acceleration that is acting, that's moving it? Well, it's the acceleration due to gravity. Okay. So the net force is what's causing everything to move downward, or the left hand to move downward and the right hand to move upward. And it's just the mass times acceleration due to gravity. That's the net force. Well, the acceleration is what we can measure, as I just pointed out, through the kinematic equations as the final velocity divided by the time. So we have this relationship that the net force is also going to be equal to, well, there's only one net force, and it's causing everything to move. And everything is moving according to this acceleration that we measure from the experiment using the kinematic equation right there. Okay, so this is the big connection point here. This experimental acceleration that we measure is accelerating the entire mass on both sides. So this mass plus this mass is m total. And it's under this constant acceleration that we can measure. Now this is the net force, and there's only one net force. And so we take the net force that we got here with a tiny bit of extra mass right here, m fall, acting under the acceleration of gravity, but it's applied to this large mass, m total. And the whole thing is just really accelerating at this slow rate of a right there. So those are the same force though. So we have the tiny mass, m fall, being accelerated by gravity, but that force is applied to the total mass right there. And of course everything is being accelerated according to A that we measure and we can calculate from the kinematic equations. So that's the remarkable connection here to make from the Atwood machine, is two different ways of measuring the same net force and setting them equal because they're the same thing. They have to be equal. And then you can solve for the acceleration that is due to gravity just by solving for g. And that's what the goal of the experiment is. You're going to take your total mass that's on both sides of the Atwood machine, divided by that tiny mass, the little excess mass on the left-hand side. That's a ratio. It's going to be bigger than 1. Multiply it times the acceleration that we can calculate. Remember, we made that acceleration slow on purpose so we can easily time it. Okay, and then you will get g. If everything goes according to plan, you'll get the acceleration due to gravity. That's pretty cool. So let's get to it. Okay, the first part of this little video for the actual experiment is the setup. Mention one little thing that's very important, is the pulley. So it's actually a dual pulley, and the purpose of the dual pulley is so that when you have a string hanging over both pulleys. It comes over both pulleys, as you'll see in a second, and it holds the strings far apart so that the mast hanging on this side doesn't interfere, accidentally bump on the mast on the other side. They're far apart, and so you can easily keep their motion independent and not interfering with each other. Okay, that's easy enough. The other main thing about the pulleys is that they are engineered to be very low friction pulleys. So I just give it a little push and you see how well it turns. Now, I was wondering about how the the wheels on the Hot Wheels cars, how much friction do they have, right? The axle inside those little wheels has to turn, and that's the main source of friction that would cause your results to not be able to align with theory, is the friction in the axle. Well, they turn pretty nicely though. That's why they can roll pretty smoothly for the Hot Wheels cars. But I bet they're not quite as good as these pulleys. The tiny amount of friction in these pulleys is going to be accounted for, but it doesn't take much. Okay, so that's the one thing about the setup here I wanted to mention with the pulleys. Okay, so I just did on your Atwood machine lab handout, which is on canvas, of course, for you to print out and fill in as you go through this video. I just did steps 1 through 4. 1 through 4, which is the setup with the hangers and the pulley and the string and everything. Next, I need to get number 5, which is measuring the mass of those hangers, and we're going to measure the mass precisely to at least the 100th of a gram. I'm using an electronic scale like the one you have at your place from the lab kit, but the masses are written on these pulleys, and I think these pulleys are supposed to be, yeah, they say 5 grams, but does that mean 5.0? 5.00 or what? We don't know how precise that is, so we need to measure it using the scale. Alrighty? Well, I'm out of time for today, actually. I'm not going to be able to finish the whole video, unfortunately, in one day, so I'm going to have to come back tomorrow and finish shooting this lab video for you guys. So now you'll know when you see me in a different set of clothes, it was the next day and I didn't just go change in the middle of the video for the fun of it, right? Okay, I'm back. I went from one blue shirt to another blue shirt. Trying not to be too overwhelmed by the big change. It's the next day, and we're going to be able to finish up this experiment no problem. So let's get to it. Alright, so we're on this step right here, step 5, getting the hanger masses. They're supposed to be right around 5 grams, or right at 5 grams. So my descending hanger mass is going to be this one with a little bit longer of a string hanging off of it. And so let's turn on the scale and see how much this one weighs. Alright. And, well, according to this scale, it is 4.93 grams. Notably less than the 5 grams it's advertised as, if you want very much precision. So write that down. And then my ascending mass hanger is going to be this one. It's got a little, well, actually, it's got the longer string hanging off of it. So The ascending mast has the longer string hanging off of it, and it is a whopping 4.95 grams. All right, so that's 3 significant figures. Oops, it went up to 4.96. Okay, I'll write that down. And on to the next step. The next step says 200 grams on each of the hangers. And I'm going to go ahead and measure those 200 gram masses on the scale here just to get the more precise value. Again, my scale keeps on automatically turning off. So I got 100 gram masses here, but we want to see how precise they are. If I use 2 of them, that's 200. And it's 199.15 grams is what I'm getting on this scale. Now this scale only goes up to a maximum of 200 grams, so I've got 199.15. I record that in the data table, the last sheet on the experiment here on the lab sheets, the last one. So M ascend is going to be 200, or actually 199.15. Plus the mass of the ascending hanger, which is the 4.96 that we just now measured as well. So that's what we have. I just wrote down these two, add them up to get the total ascending mass, or the ascending mass. And that's going to stay constant throughout the experiment, so we're just going to be altering the descending mass. And of course then the total mass will be changing as this changes, and then the mass that's falling, which is causing the whole system to move or accelerate, is going to be changing. So let's see about that. First I'm going to put these, see, I told you this scale keeps on turning off automatically on me for some reason. It's annoying. I'm going to put these onto the ascending hook. Got a nice little hole on them here so that it holds them and they won't bounce off whenever if the hook hits the table, it won't bounce off. Now I need to do this for the descending hanger, and I got another 2 100 gram masses here. I'm going to put them on. Now whenever I measure these on the scale, these are supposed to be pretty precise. So this coming up is 199.15 for the first one. It's a little suspicious because that's in the limit of its maximum range. But that's the scale I got. I probably should maybe go find another one to get some confirmation. But this one's coming out 199.28, and that's going to be going on to the other side. I'm going to write it right here. Initially that's the descending mass, but I'm going to add a little bit more, as you'll see in the upcoming procedure, to make everything descend. Okay. Now I'm going to add these 2 masses onto here, and they are hanging on the Atwood machine here. You see them on the pulley. So let's get the full view. Apparently those strings were rather twisted up, and they're now untwisting. But you can see that this goes up and down very easily, either direction, either side I should say. So it's, like we mentioned earlier, very low friction pulleys. And the next part is where the sensitivity is put to the test, where we have to get this thing to descend. Well, this is my descending side with the shorter string on it right here. And so I'm going to start it at the highest point and then make it descend with a tiny push, and ideally it will descend at a constant speed Right now it stopped, so it's not ideal. That means that there's friction and inertia in the pulleys. Remember, that's Newton's first law, is the law of inertia. So the pulleys resist being turned. They have inertia. They resist starting turning and any changes in their motion, and so that can slow it down. And of course, they have some friction in them. And these two sides, the masses aren't exactly the same. So when I give it a little push, it goes for a long ways, almost all the way, and then it stops. Okay, so there's a little bit of friction and things that is unaccounted for. Although it's close, so there's not much difference here. Okay, I gave it a tiny push, you see it went and it stopped, okay? I give it a tiny little push again, and there must be some imbalance maybe in the pulleys or something with how they're aligned that can also cause it to stop. And then it bounces back a little bit, interestingly enough. But it is close to almost going down at a constant speed, and that's the key part. Alright, I got the ruler in place now so we can measure the height that the descending mass is going to fall from. Let's get a closer look on that. And you guys can write down that measurement. Oops, sorry for the shakiness here. So it's coming up, and the first part of the descending mass, the hanger that's going to hit the ground or hit the tabletop, is that point right there probably. So you got to measure 70, 1, 2, 3, 4, 5, and then there's going to be some parallax errors here, perhaps, where we can't quite align it, but it's 75 point something. And you guys can decide exactly what you think it is. I can maybe move it at a different angle so we can see that scale lining up with the lowest point on the hanger. We can get at least 3 significant figures for the height of the fall. Alright, so I'll go ahead and tell you I measured it, as you could see, pretty close. 75.5 centimeters, which of course is 0.755 meters for the distance of the fall. Now the next part is a little bit intimidating if you're reading through these directions and doing them yourself. It may take a little while to figure out what's going on here, but all of this is written out in an order to find what I call MFPI. M, the little subscripts FPI. That is the mass on the side that is going to be descending that counts for friction of the pulley and its inertia. Okay, so on the descending side, like I was saying earlier, if I give it a tiny little push, it doesn't freely fall all the way down, because friction in the pulley and inertia and any other little factors causes it to stop, and we want it to be able to fall freely, so that the only thing that is affecting it is the acceleration due to gravity. So in order to compensate for friction in the pulley and inertia of the pulley, we're adding what is referred to as the MFPI on the lab handout. It's a tiny bit of extra mass added on the descending side that will overcome the friction and allow it to, with the tiniest push, it will allow this side to go all the way down to the table. So I'm going to start out with a little bitty, I think this is supposed to be a ½ gram mass right here. I'm just going to add it to this hook and see if that is enough to overcome any apparent friction in the pulley and other effects. So add a tiny little push, and does it go all the way down at a constant rate? Oh, pretty. Oh, it's going, and it's almost stopping, but it keeps going. It stopped. So that was very close to going all the way down. Normally it doesn't. It takes a gram or 2 to overcome the friction in the pulley and everything. So now I'm going to take off this 1/2 gram mass, and instead I'm going to go to the 1 gram mass and see if that's enough to overcome it. Okay, so, oops, it come off the string come off the pulley right there. That happens sometimes. Let me check it. The pulley is very well aligned. Okay, so now if we start it all the way at the top, I'm going to give it a tiny little push, and we will see if it goes all the way down smoothly. Tiny little start, push it down, and it keeps going, and it's looking like it's keeping on going for sure. And I couldn't really see an acceleration. There was perhaps a very, very tiny acceleration on the descending side. But because 0.5 grams didn't quite allow it to go all the way down, and 1 gram does allow it to go all the way down, we could assume that the mass required to overcome all those inertia and friction effects is just in between 1 and 0.5. You know. So let me try one more time. A tiny little push, and it keeps on going. At a very constant rate, so that's good. We hit that extra little bit of weight to overcome friction pretty precisely with a 1 gram mass. All right, so now I'm going to measure it on the scale here to see exactly what that comes out to be. Okay, here's that 1 gram mass. Put it on there and see what it comes up. Comes up as, well, 1.00 grams with 3 significant figures. So that's MFPI is what we call it in the lab sheets. Okay, now the point of this extra little 1 gram mass added on the descending side is to overcome, the friction and inertia, like I said 100 times already, right? Now, what I wanted to mention also is, though we have it on there, we ignore it from this point on. We pretend that it's not there, just like we want to pretend that friction and inertia is not there, because we want the system to be independent of that. So that mass overcame it, the friction and inertia, so we just say, okay, we're going to ignore it from now on. The next step is to get a 2 gram mass and add it to the descending side and measure the time it takes for it to fall under the acceleration of nothing but gravity, right? So I got a 2 gram mass right here, and I'm going to measure its precise value on the scale here and write it down, and I'll give it to you guys in just a second. All right? And what you're going to do for the rest of this video is I'm going to add the mass required onto the descending side, and I'm going to start it, or no, I won't have to start it. Because it's going to have that extra mass on here, it will start accelerating all on its own after I release it. Alright, so you all are going to actually time how long it takes to go from, the starting height to the tabletop. And you have to do this at home with your own timers while you're watching the video. That's the plan, at least. I will time it here as well with a stopwatch or something, and you guys will hopefully find the same times. So let me measure this real quick. It comes out to be a good 2.01 grams. Okay. So I'm going to add it to the descending side. I'm going to start it from its maximum height that we measured earlier with the ruler or the meter stick. I'm going to release it, and I will say the word release, and then you will start your timer, and when it hits the table, you will stop your timer and write down the time on the data sheet, okay? Actually, I can hold it down here and release it from the bottom more easily. Ready? Okay. 1, 2, 3, release. Starting out very slowly, but you see it's accelerating. Bam! Okay, did you get that time? So that's the fall times. I'm going to do, apparently on the data sheet, it's got a space for 5 fall times for each of the different masses that we're going to add to the descending side. So let me show you, here's the mass that we have on the descending side. The hanger mass, which is what we measured at 4.93 grams. The 200 grams that we added is 199.28. And the mass that is falling, the little extra bit that we added, is 2.01 grams. Now remember that mass FPI, the MFPI, is ignored. Okay, so we don't include it in here for the descending mass. So that's what we write in the table for the descending mass, is the total of all of those. So M descending is all of these, right? You put that in the table right here, M descending, and then M total is going to be all of that M descending plus all the ascending mass that is on the opposite side of the pulley. Okay, and then M fall is just that little 2.01 that I just now measured. That little bitty mass, 2.01 grams, well, it says in kilograms, so you have to convert that, move the decimal 3 places over. Let me go ahead and do that for a reminder. It's actually 0.00201. So it's a small number of kilograms. Okay? That little amount is moving all of this mass plus all of the descending mass, right? Over 400 grams is being moved by 2 grams under the acceleration of gravity. Okay? But because all that mass is being moved by a tiny little mass with the acceleration of gravity, it's acting on all of that mass. It accelerates slowly, and we can time it. So let's do some more times. Okay, so that first one was a bonus one. I didn't time it myself, so I don't know what that first time was. But now we're going to do 5 in a row, and I'm going to time it. I got a little stopwatch here that I'm going to use, and you can use your cell phone timer or whatever you have handy, and do these 5 in a row real quick. Ready, set, go. Two. Okay, I got that time. And it's taking a long time with this tiny little mass, but you'll see when we add more that it will not take nearly as long. Okay? It'll start to go much shorter times. Okay, now I'm starting it from the tabletop. I make sure that it's starting from the tabletop. Ready, set, go. I think you could hear that hitting the table pretty easy. Let me replay and see. Okay, so you could hear that, and you know what's pretty remarkable here is that my time came out to be almost exactly to the 100th of a second, the same as the first trial for this mass, or this mass that's falling. So let's do the third one here. And ready, set, and go. Oh my gosh. Unbelievable. I got the exact same time to the 100th of a second for this thing hitting the table surface. That's precise right there, or well, consistency. Which is good, but you know, consistent doesn't necessarily mean accurate. You can be consistently wrong on something, right? So, anyways, let's try the third. No, this is the fourth trial. Ready, set, and go. Pretty consistent with the previous one. Okay, trial number three. Trial number three for the total falling mass of 6.03 grams. Are you ready? Ready, set, go. Go! Oh, that was a good one. Okay, I got that one. Back on there. You know, I had thought I could just make all these measurements myself, and I could put the video in fast motion for you guys to just watch me do all this myself. And then I would just show you my measurements. But that would take the joy of it away from you a little bit, right? This is exciting, watching this thing fall and having to time it on the video. That's exciting. That's much better. So, trial number 4. Ready, steady, go. Oh no, one crashed off the table. Ah. Right, ready for the last trial? On your marks. Get set. Go! Oh yeah, that was the shortest time of them all. But it wasn't too short to be inconsistent. It was still quite consistent with the previous one. So that's fitting. The last trial was the shortest one. Okay, that's all the measurements for the whole experiment. You should have all the data you need now to do all the calculations. Alright, I wanted to make sure that everyone at least gets the masses all correct for this experiment. So I'm going to add these up and show them on the data table in a second here for all the masses that you should have and use for the rest of the calculation. So the descending mass starts out at 206.22 grams. Okay, so I'm going to put that on the data table here. Alright, so on here we have 206.22 for the first value in the table. Now it's kilograms, oops, so put a 0 point right there, 0.20622. Now that's 5 significant figures. That's way more than enough significant figures. But there they are. Now the M total is going to be the ascending mass plus this. So the ascending mass is 204.11. That's what that equals. And we add those two numbers together. Of course, it comes out to 410.33. So on the kilogram scale, you have 0.41033. And the mass that was falling, oops, those are I don't want you to see my fall times that I measured. Got those blocked here, but you can see the falling masses that added up as we went through the experiment here. And the M total is just going to be increasing by this amount every single time. So we added 1 gram on, so this is going to be 20723. No. 722, just as we didn't add another. We just went up by 1 gram exactly. So it just goes up 1 here and 1 here, so it's a lot of redundancy on the writing, but okay. It's going to go up by 1 gram here, so it's going to be 133 on that one. Okay, now you have all those masses. Everybody should be on the same page for those. MFPI up here was 1.00. Alright. And the descending and ascending hangers, we measured those. You can write those up there as well. Then you have your fall times that you measure from the video right there. Get their average values, and then you come down here and do the calculations. Now these calculations for table 2, the formulas you need are all down here. They're also written in, you know, the first part of this video for the PowerPoint slides. You know, it goes through how to do these calculations or shows the formulas for them. So, but it's written down here, your measured distance divided by the average time, that's your average velocities. Final velocities, just 2 times that, you record those, so it should be very easy to go through and calculate all these. And it'll come out to be experimental force in newtons, and then you can get your experimental gravity by the ratio of those masses like I showed in the PowerPoints, multiplied by the experimental acceleration. So you're going to go through and do those calculations. And then you're going to do a graph. So you'll get the average from these up here. That's one way of getting should be a good experimental acceleration due to gravity. And percent error compared to the expected or accepted value right there. But for the graph, I will give you bonus points if you do this graph on Excel and make it look nice. And of course it has all the needed components. Otherwise you can do it by hand on this little graph paper here. So for the graph you're going to have to use this experimental force in newtons. Now it's going to be a small number of newtons. It's not a big force. It's caused by the by the falling mass. So of course the falling mass is going to be these values right here. So that's going to be the x-axis, the falling mass in kilograms, and the y-axis on their graph is going to be the experimental force in newtons. So the force is going to be rising up as the mass increases, or however you do the scale here is up to you. But when you take that slope, that's going to be force divided by mass, and from Newton's second law, you know that you have, acceleration is going to be equal to force over mass. Or for us, because it's going to be the force due to gravity and the mass that's causing that force, it's going to be equal to g from the graph. And that should give you a value very similar to the average g that you calculate for each individual trial. So that's it for this video. I hope you guys learned a good bit and enjoyed this lab, and I'll see you in the next one.